A dust explosion is the rapid combustion of fine particles suspended in the air, often but not always in an enclosed location. Dust explosions can occur where any dispersed powdered combustible material is present in high enough concentrations in the atmosphere or other oxidizing gaseous mediums such as oxygen. Dust explosions are a frequent hazard in underground coal mines, in grain elevators, and other industrial environments. On the other hand, they are also commonly used by special effects artists, filmmakers, and pyrotechnicians, given their spectacular appearance and ability to be safely contained under certain carefully controlled conditions. Terminology: if rapid combustion occurs in a confined space, enormous overpressures can build up, causing major structural damage and flying shrapnel. The sudden release of energy from a detonation can produce a shock wave either in open air or in a confined space. If the spread of flame is at subsonic speed, the phenomenon is sometimes called a deflagration, although looser usage calls both phenomena explosions. Dust explosions may be classified as being either primary, or secondary in nature. Primary dust explosions may occur inside process equipment or similar enclosures, and are generally controlled by pressure relief through purpose-built ducting to the external atmosphere. Secondary dust explosions are the result of dust accumulation inside a building being disturbed and ignited by the primary explosion, resulting in a much more dangerous uncontrolled explosion inside the workplace. Historically, fatalities from dust explosions have largely been the result of secondary dust explosions. Conditions required. There are 4 necessary conditions for a dust explosion: A. Combustible dust. The dust is suspended in the air at a sufficiently high concentration, there is an oxidant, there is an ignition source. In some traditional analyses of dust explosions, confinement is considered to be a 5th requirement. This is not an essential condition, but can greatly aggravate the physical damage that results. Sources of dust equals. Many common materials which are known to burn can generate a dust explosion, such as coal and sawdust. In addition, many otherwise mundane organic materials can also be dispersed into a dangerous dust cloud, such as grain, flour, starch, sugar, powdered milk, cocoa, coffee, and pollen. Powdered metals can form explosive suspensions in air, if finely divided. Explosive dust can arise from activities such as transporting grain, and grain silos have often been demolished violently. Mining of coal leads to coal dust, and flour mills likewise have large amounts of flour dust as a result of milling. A gigantic explosion of flour dust destroyed a mill in Minnesota on May 2, 1878, killing 14 workers at the Washburner Mill, and another 4 in adjacent buildings. A similar problem occurs in sawmills and other places dedicated to woodworking. Although not strictly a dust, paper particles emitted during processing, especially rolling, unrolling, calendaring, slitting, and sheet cutting, are also known to pose an explosion hazard. Enclosed paper mill areas subject to such dangers commonly maintain very high air humidities to reduce the chance of airborne paper dust explosions. In special effects pyrotechnics, lycopodium powder and non-dairy creamer are 2 common means of producing safe, controlled fire effects. Thermobaric weapons, depending upon their fuel, are also a potential and intentional source of dust. To support rapid combustion, the dust must consist of very small particles with a high surface area to volume ratio, thereby making the collective or combined surface area of all the particles very large in comparison to a dust of larger particles. Dust is defined as powders with particles less than about 500 micrometers in diameter, but finer dust will present a much greater hazard than coarse particles by virtue of the larger total surface area of all the particles. Concentration equals, below a certain value, the lower explosive limit, there is simply insufficient dust to support the combustion at the rate required for an explosion. A combustible concentration at or below 25% of the LEL is considered safe. Similarly, if the fuel-air ratio increases above the upper explosive limit, there is insufficient oxidant to permit combustion to continue at the necessary rate. Oxidant equals, Typically, normal atmospheric oxygen can be sufficient to support a dust explosion if the other necessary conditions are also present. High oxygen or pure oxygen environments are considered to be especially hazardous, as are strong oxidizing gases such as chlorine and fluorine. Also, particulate suspensions of compounds with a high oxidative potential, such as peroxides, chlorates, nitrates, perchlorates, and dichromates, can increase risk of an explosion if combustible materials are also present. Equal sources of ignition equals, there are many sources of ignition, and a naked flame need not be the only one. Over one-half of the dust explosions in Germany in 2005 were from non-flame sources. Common sources of ignition include electrostatic discharge, friction, electrical arcing from machinery or other equipment, hot surfaces, fire. However, it is often difficult to determine the exact source of ignition when investigating after an explosion. When a source cannot be found, ignition will often be attributed to static electricity. Static charges can be generated by external sources, or can be internally generated by friction at the surfaces of particles themselves as they collide or move past one another. Mechanism: dusts have a very large surface area compared to their mass. Since burning can only occur at the surface of a solid or liquid, where it can react with oxygen, this causes dusts to be much more flammable than bulk materials. For example, a 1 kg sphere of a combustible material with a density of 1 gram per centimeter 3 would be about 12.4 centimeters in diameter, and have a surface area of 0.048 square meters. However, if it were broken up into spherical dust particles 50 micrometer in diameter, it would have a surface area of 120 square meters. This greatly increased surface area allows the material to burn much faster, and the extremely small mass of each particle allows them to catch on fire with much less energy than the bulk material, as there is no heat loss to conduction within the material. When this mixture of fuel and air is ignited, especially in a confined space such as a warehouse or silo, a significant increase in pressure is created, often more than sufficient to demolish the structure. Even materials that are traditionally thought of as non-flammable, or slow-burning, can produce a powerful explosion when finely divided, and can be ignited by even a small spark. Demonstration of an open-air dust explosion. Effects: a dust explosion can cause major damage to structures, equipment, and personnel from violent overpressure or shock wave effects. Flying objects and debris can cause further damage. Intense radiant heat from a fireball can ignite the surroundings, or cause severe skin burns in unprotected persons. In a tightly enclosed space, the sudden depletion of oxygen can cause asphyxiation. Protection and mitigation. Much research has been carried out in Europe and elsewhere to understand how to control these dangers, but dust explosions still occur. The alternatives for making processes and plants safer depend on the industry. In the coal mining industry, a methane explosion can initiate a coal dust explosion, which can then engulf an entire mine pit. As a precaution, incombustible stone dust may be spread along mine roadways, or stored in trays hanging from the roof, to dilute the coal dust stirred up by a shock wave to the point where it cannot burn. Mines may also be sprayed with water to inhibit ignition. Some industries exclude oxygen from dust-raising processes, a precaution known as inerting. Typically this uses nitrogen, carbon dioxide, or argon, which are incombustible gases which can displace oxygen. The same method is also used in large storage tanks where flammable vapors can accumulate. However, use of oxygen-free gases brings a risk of asphyxiation of the workers. Workers who need illumination in enclosed spaces where a dust explosion is a high risk often use lamps designed for underwater divers, as they have no risk of producing an open spark due to their sealed waterproof design. Good housekeeping practices, such as eliminating buildup of combustible dust deposits that could be disturbed and lead to a secondary explosion, also help mitigate the problem. Best engineering control measures which can be found in the National Fire Protection Association combustible dust standards include wetting, oxidant concentration reduction, deflagration venting, deflagration pressure containment, deflagration suppression, deflagration venting through a dust retention and flame arresting device. Notable incidents: dust clouds are a common source of explosions, causing an estimated 2,000 explosions annually in Europe. The table lists notable incidents worldwide. See also, air-to-fuel ratio, coal dust, combustion, explosion vent, flower bomb. References: John Barton, Dust Explosion Prevention and Protection Institution of Chemical Engineers, Rugby 2002, ISBN 0-85295-410-7. Rolf K. Eckhoff, Dust Explosions in the Process Industries, 2nd ed. Butterworth Heinemann, Oxford 1997, ISBN 0-7506-3270-4. External links: Incidents in France and the U.S., Combustible Dust Explosion Investigation Products from the Chemical Safety Board, Combustible Dust Policy Institute ATEX, OSHA Case Studies of Dust Explosions, Protecting Process Plant and Grain Handling Facilities from the Risk of Dust Hazard Explosions, Dust Explosions, the Dangers, and the Precautions Needed to Avoid Them, Hazard Monitoring Equipment, Selection, Installation and Maintenance, Seminars for Combustible Dust Safety, FAQs, Solutions for Minimizing Dust Explosion Risks.